I'm so glad you found your way here. Maybe you had a long day, or maybe you're the kind of person who likes falling asleep to deep thoughts and cosmic mysteries rather than counting sheep. Either way, tonight's journey is for you. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light as if time itself has softened. Because tonight, we aren't simply exploring space. We're traveling backward through time itself, to the very beginning of everything. To the moment when there was no space, no time, no matter, no light. And then, in an instant almost too brief to imagine, everything began. The Big Bang. Not an explosion in the usual sense, but something far stranger. The birth of reality itself. Some of what you hear tonight may surprise you or at the very least spark some curiosity as you drift off to sleep. And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too. One sleepy soul at a time. Now, let's begin. The Big Bang was not an explosion in space. When most people hear the term Big Bang, they imagine a massive explosion, like a bomb detonating in empty space, flinging matter outward into a pre-existing void. But that picture is wrong. The Big Bang was not an explosion in space. It was the expansion of space itself. Before the Big Bang, there was no space to explode into. No darkness waiting, no stage upon which the drama would unfold. Space itself came into being in that moment, and it has been expanding ever since. Every point in the universe was once the same point. Everything that exists, every galaxy, every star, every atom in your body, was compressed into something unimaginably small. And then space began to stretch, carrying everything with it, not outward into something, but outward as something. The fabric of reality itself unfurling like a flower opening in the morning light. The universe began from a singularity. At the very beginning, all the matter and energy that would ever exist was compressed into an infinitely small, infinitely dense point called a singularity. Temperature, density, and curvature of space-time were infinite. The laws of physics as we know them did not apply. General relativity tells us that at this point, space-time itself becomes so warped that our equations break down. We cannot describe what happened at time zero. We cannot peer into the singularity itself. It is a boundary beyond which our current understanding cannot pass. But we can get very, very close. Within the tiniest fraction of a second after the beginning, we can trace the universe's evolution with remarkable precision. That singularity, that point of infinite mystery, gave birth to everything. To time, to space, to possibility itself. We cannot know what happened before the Planck time. The Planck time is the smallest meaningful unit of time in physics, approximately 10 to the negative 43 seconds. That's a decimal point followed by 42 zeros and then a 1. Unimaginably brief. Before this moment, quantum effects dominate gravity so completely that space-time itself becomes a seething, uncertain foam. Our theories of physics, both quantum mechanics and general relativity, fail to describe what happened. They give us nonsense answers, infinities, contradictions. So when we speak of the Big Bang, we're really speaking of everything that happened after the Planck time. The first trillionth of a trillionth of a trillionth of a second remains veiled. What came before, if before even has meaning, we do not know. Perhaps there was no before. Perhaps time itself began at the Big Bang. Or perhaps our universe emerged from something else entirely, a quantum fluctuation, a collapsing previous universe, a higher dimensional structure we cannot yet conceive. The very beginning remains wrapped in mystery. Inflation stretched the universe exponentially. In the earliest moments, something extraordinary happened. The universe didn't just expand, it inflated. Between approximately 10 to the negative 36 seconds and 10 to the negative 32 seconds after the Big Bang, the universe doubled in size at least 90 times. Imagine a balloon inflating, but instead of taking minutes, it happens in a time span so brief that light can barely move at all. A region smaller than a proton swelled to the size of a grapefruit, or perhaps much larger in an instant. This period of cosmic inflation was driven by a mysterious field, often called the inflaton field, which filled space with a kind of repulsive gravity. Space expanded faster than the speed of light. This doesn't violate relativity, because nothing was moving through space faster than light. Space itself was expanding, carrying everything with it. When inflation ended, the energy driving it transformed into matter and radiation, reheating the universe and beginning the hot, dense phase we typically call the Big Bang. Inflation happened so fast that it froze quantum fluctuations into the fabric of space. Inflation solves several deep cosmic puzzles. Before inflation was proposed, cosmologists struggled with what's called the horizon problem. When we look at the cosmic microwave background, the afterglow of the Big Bang visible in all directions, we see that it has almost exactly the same temperature everywhere. It varies by only 1 part in 100,000. This is puzzling because regions of the sky on opposite sides of the universe are so far apart that light hasn't had time to travel between them since the Big Bang. They should never have been in contact. So why do they have the same temperature? Inflation solves this. Before inflation, the entire observable universe was once a tiny region, small enough that it could smooth itself out, reach thermal equilibrium. Then, inflation stretched this tiny, uniform patch to enormous size, much larger than what we can now observe. The universe looks the same in all directions because it all came from the same small, well-mixed beginning. Inflation also explains the flatness problem. The universe appears to be geometrically flat, meaning parallel lines stay parallel forever, like on a sheet of paper rather than curving like on a sphere or saddle. But for the universe to be this flat today, it had to be incredibly, impossibly flat in the early moments. Inflation explains this naturally. No matter what shape space had before inflation, the exponential expansion stretched it so much that it became flat, the way the surface of a balloon looks flat if you inflate it enough. These aren't just theoretical niceties. They're profound explanations for why our universe looks the way it does. The 4 fundamental forces were once unified. Today, we know of 4 fundamental forces that govern everything in the universe. Gravity, which holds planets in orbit and pulls galaxies together. Electromagnetism, which governs light, electricity, and chemistry. The strong nuclear force, which binds quarks into protons and neutrons and holds atomic nuclei together. And the weak nuclear force, which governs certain types of radioactive decay. But in the extreme conditions of the very early universe, these forces were not separate. At the highest energies, they were unified into a single force. As the universe expanded and cooled, these forces split apart one by one in a process called spontaneous symmetry breaking. First, gravity separated from the other forces at around the Planck time, 10 to the negative 43 seconds. Then, the strong nuclear force split off around 10 to the negative 35 seconds. Finally, The electromagnetic and weak forces, which were unified into the electroweak force, separated around 10 to the negative 12 seconds, when the universe was merely a trillionth of a second old. These separations released enormous amounts of energy and fundamentally changed how particles interacted. The universe went through a series of phase transitions, like water freezing into ice, except far more profound. Each transition left its mark on the structure and contents of the cosmos. The universe was once unimaginably hot. Temperature is a measure of how fast particles are moving and vibrating. In the earliest moments after the Big Bang, the universe was the hottest it would ever be. At 10 to the negative 43 seconds, the Planck time, the temperature was approximately 10 to the 32 degrees Kelvin. That's a 1 followed by 32 zeros. To put this in perspective, the core of the Sun is about 15 million degrees Kelvin. The early universe was trillions of times hotter. At these temperatures, particles had so much energy that even fundamental particles couldn't form stable structures. Everything existed as a seething soup of energy and fleeting quantum fluctuations. As the universe expanded, it cooled. The temperature dropped exponentially. By 1 second after the Big Bang, it had cooled to about 10 billion degrees. Still incredibly hot, hotter than the core of the most massive stars, but cool enough for protons and neutrons to hold together. By the time the universe was 3 minutes old, it had cooled to about 1 billion degrees. And after 380,000 years, it had cooled to about 3,000 degrees, cool enough for atoms to form. Today, the average temperature of the universe is just 2.7 degrees above absolute zero, the cosmic microwave background radiation that fills all of space. The universe has been cooling for nearly 14 billion years, and it will continue to cool forever. Particles and antiparticles annihilated each other. In the very early universe, conditions were so energetic that particles and their antimatter counterparts were constantly being created and destroyed. For every type of particle, there is an antiparticle with the same mass but opposite charge. When a particle meets its antiparticle, they annihilate, converting their mass entirely into energy according to Einstein's famous equation, E equals mc squared. In the first moments, this happened constantly. Photons, particles of light, had so much energy that they could spontaneously create particle-antiparticle pairs, which would then annihilate back into photons. The universe was a roiling sea of creation and destruction, matter appearing and disappearing in endless cycles. But there was a crucial asymmetry. For every billion antiparticles, there were about 1,000,000,001 particles of ordinary matter. This tiny imbalance, just 1 part in a billion, seems insignificant. But it's the reason we exist. As the universe expanded and cooled, most of the matter and antimatter annihilated, filling space with enormous numbers of photons. But that tiny excess of matter survived. The one extra matter particle for every billion pairs had nothing to annihilate with. These leftovers became everything we see today. Every star, every planet, every atom in your body exists because of this mysterious asymmetry. Why matter slightly outnumbered antimatter remains one of the great unsolved questions in physics. We exist because of a cosmic imbalance. The matter-antimatter asymmetry is called baryogenesis, the creation of more baryons, particles like protons and neutrons, than antibaryons. Without this asymmetry, the universe would be filled only with light, photons left over from perfect annihilation, with no matter to form stars, planets, or people. several conditions must be met for baryogenesis to occur. First, there must be processes that violate baryon number conservation, allowing the number of matter particles to change. Second, there must be a violation of charge and parity symmetry, meaning the laws of physics treat particles and antiparticles slightly differently. Third, these processes must occur out of thermal equilibrium, meaning the universe must be changing faster than reactions can keep up. All three conditions, known as the Sakharov conditions, were met in the early universe. Various theories attempt to explain exactly when and how the asymmetry arose. Some invoke physics beyond the standard model. Others point to processes during the electroweak phase transition, or even earlier during inflation. We've observed that certain weak force interactions do treat matter and antimatter differently, but not by enough to explain the full asymmetry. The answer likely lies in physics we haven't yet discovered, possibly involving very massive particles that existed only in the earliest moments and whose decay produced more matter than antimatter. It's humbling to think that our existence hinges on this delicate imbalance, this 1 part in a billion excess that survived the annihilation. Quarks combined to form protons and neutrons. In the first microseconds, the universe was so hot that quarks, the fundamental building blocks of protons and neutrons, could not bind together. They existed in what's called a quark-gluon plasma, a state of matter so energetic that quarks roamed freely, held loosely together by gluons, the particles that carry the strong nuclear force. This plasma filled all of space, a primordial soup of the most fundamental particles. But as the universe expanded and cooled, reaching a temperature of about 2 trillion degrees Kelvin around 10 microseconds after the Big Bang, quarks began to confine. The strong force, which becomes stronger at larger distances, pulled quarks together into bound states. 3 quarks combined to form protons and neutrons, collectively called baryons. This process, called quark confinement, marked a fundamental transition. Before, the universe was made of free quarks and gluons. After, it was made of composite particles, the protons and neutrons that would eventually form atomic nuclei. This transition wasn't smooth. It was a phase change, like water suddenly freezing into ice, and it fundamentally altered the nature of matter in the universe. From this point forward, quarks would be permanently locked inside protons and neutrons. We've never observed a free quark in nature. They exist only within these bound states, hidden inside the particles that make up everything around us. The neutron-to-proton ratio determined the universe's composition. In the first second after the Big Bang, neutrons and protons were in thermal equilibrium, constantly converting into each other through weak force interactions. Neutrons could decay into protons, and protons could capture electrons to become neutrons. The balance between these processes depended on temperature. Initially, there were roughly equal numbers of neutrons and protons. But neutrons are slightly heavier than protons, and as the universe cooled, it became energetically harder to create neutrons. By the time the universe was about 1 second old, the temperature had dropped enough that these conversion processes essentially stopped. The ratio of neutrons to protons was frozen at about 1 neutron for every 7 protons. This ratio would prove crucial. Neutrons are unstable when free, decaying into protons with a half-life of about 10 minutes. So, between 1 second and a few minutes after the Big Bang, some neutrons decayed, shifting the ratio further. By the time the universe was cool enough for nuclear fusion to begin, the ratio had shifted to about 1 neutron for every 7 protons, or roughly 12% neutrons. This ratio determined how much of each element would form in the early universe. Nearly all the remaining neutrons would be locked into helium nuclei, which contain 2 protons and 2 neutrons. The math works out such that about 25% of ordinary matter by mass became helium, with the rest remaining as hydrogen. This prediction, made decades ago, matches observations with stunning precision. Everywhere we look in the universe, the oldest, most pristine gas clouds contain about 75% hydrogen and 25% helium by mass, exactly as predicted by Big Bang nucleosynthesis. Neutrinos decoupled and now fill the universe. Neutrinos are among the strangest particles in physics. They have almost no mass, no electric charge, and interact so weakly with matter that trillions pass through your body every second without you noticing. They're produced in nuclear reactions, in the sun, in supernovae, and in the Big Bang itself. In the very early universe, when everything was packed incredibly densely, even neutrinos interacted frequently with other particles. But around 1 second after the Big Bang, when the universe had expanded and cooled enough, neutrinos decoupled. They stopped interacting with other matter and began streaming freely through space. This cosmic neutrino background, analogous to the cosmic microwave background but even older, still exists today. The universe is filled with relic neutrinos from that first second, cooled now to just a couple degrees above absolute zero. There should be about 300 million neutrinos per cubic meter of space, vastly outnumbering atoms. But they're extraordinarily difficult to detect. We've never directly observed the cosmic neutrino background, though we're certain it exists. These neutrinos carry information from the very first second of the universe, a time earlier than any light can show us. If we could detect them, they would open a window into the universe at an age of just 1 second old, revealing conditions and processes hidden from all other observations. They are whispers from the beginning, ghostly messengers that have been traveling through the cosmos for nearly 14 billion years. Big Bang nucleosynthesis forged the first elements. Between about 10 seconds and 20 minutes after the Big Bang, the universe underwent one of its most important transformations. The temperature and density were finally right for nuclear fusion to occur. This period, called Big Bang nucleosynthesis, or primordial nucleosynthesis, was when the first atomic nuclei formed. Before this, it was too hot. Any nuclei that formed would be immediately blasted apart by high-energy photons. After this window closed, it was too cool and too diffuse for fusion to continue. But for a few precious minutes, conditions were similar to those in the cores of stars, and fusion could proceed. Protons and neutrons combined to form deuterium, a heavy form of hydrogen with 1 proton and 1 neutron. Deuterium nuclei then fused to form helium-3, which has 2 protons and 1 neutron, and helium-4, which has 2 protons and 2 neutrons. Small amounts of lithium-7 also formed. The process was remarkably efficient. Nearly all the remaining neutrons ended up in helium-4 nuclei, because helium-4 is extremely stable and was the easiest nucleus to form under those conditions. When the fusion ended, about 75% of ordinary matter by mass was hydrogen, single protons, and about 25% was helium-4. There were also trace amounts of deuterium, helium-3, and lithium-7, each at levels of about 1 part in 100,000 or less. These ratios depend very sensitively on conditions in the early universe, particularly the density of ordinary matter and the number of neutrino types. The fact that observations match predictions so precisely is one of the strongest confirmations of the Big Bang theory. The early universe could not make carbon. You might wonder, if fusion was happening in the early universe, why did it stop at helium and lithium? Why weren't heavier elements like carbon, oxygen, and iron produced then? The answer lies in the peculiarities of nuclear physics and the rapid expansion of the universe. To build carbon, you need to fuse 3 helium-4 nuclei together in what's called the triple alpha process. But this requires very specific conditions of temperature, density, and time that didn't exist in the early universe. First, there's no stable nucleus with 5 or 8 nucleons, which means you can't build carbon by simply adding protons or neutrons to helium one at a time. You need 3 helium nuclei to come together almost simultaneously. This is extraordinarily unlikely unless the density is high and stays high for a long time. In the early universe, the density was dropping too rapidly. By the time enough helium had formed, the universe had expanded and cooled too much for triple alpha fusion to occur. The window for nucleosynthesis closed after just a few minutes, and no elements heavier than lithium formed in significant quantities. This means the carbon in your body, the oxygen you breathe, the iron in your blood, none of it came from the Big Bang. These elements would have to wait hundreds of millions of years until the first stars formed, lived, and died, forging heavy elements in their cores and scattering them through space in supernova explosions. We are made of stardust, not Big Bang dust. The 75-25 ratio is a cosmic signature. One of the most remarkable predictions of Big Bang theory is the ratio of hydrogen to helium in the universe. According to the physics of the first few minutes, about 75% of ordinary matter by mass should be hydrogen, and 25% should be helium-4. This isn't just a rough estimate. It can be calculated quite precisely based on the conditions in the early universe, and the match between prediction and observation is stunning. When astronomers measure the composition of the oldest stars, those formed shortly after the Big Bang from pristine gas, untouched by stellar processing, they find that the helium abundance is about 24 to 25% by mass. When they measure the composition of distant gas clouds that have never formed stars, they find the same thing. Everywhere they look, in every direction, across billions of light years, the primordial helium abundance is right around 25%. The trace amounts of deuterium and helium-3 also match predictions. This agreement is one of the most powerful pieces of evidence for the Big Bang. No other theory explains why the universe should have this particular composition. In steady-state models, where the universe has always existed in roughly its current form, there's no mechanism to produce helium in these proportions. Only the hot, dense, rapidly expanding conditions of the Big Bang can account for what we observe. The universe carries this signature in every atom, a fingerprint left by the first 3 minutes of creation. The photon epoch kept the universe opaque. After the first few minutes, nuclear fusion stopped, and the universe entered a long period called the photon epoch. Matter now consisted of nuclei, mostly hydrogen and helium, along with free electrons that hadn't yet been captured into atoms. The universe was also filled with photons, particles of light, left over from the annihilation of matter and antimatter. But these photons couldn't travel freely. Whenever a photon tried to move through space, it would almost immediately collide with a free electron. The electron would absorb the photon and then re-emit it in a random direction. This constant scattering meant that light couldn't travel far. the universe was opaque, filled with a glowing fog. If you could have been there, you wouldn't have been able to see anything. Light would scatter off electrons in every direction, creating a uniform glow with no distinct sources or shadows. This state persisted for hundreds of thousands of years. During this time, the universe continued to expand and cool, but its appearance changed little. The temperature dropped from billions of degrees to millions to hundreds of thousands, and eventually to just a few thousand degrees. The universe glowed like the surface of a star, bright and hot and completely opaque to its own light. This period is sometimes called the Dark Ages, though that name more properly applies to a later period. The universe wasn't dark. It was glowing, but it was featureless, a cosmic fog with nothing visible inside it. Recombination allowed atoms to form. Around 380,000 years after the Big Bang, something profound happened. The universe had cooled to about 3,000 degrees Kelvin, roughly the temperature of the surface of a red dwarf star. At this temperature, electrons finally had little enough energy that they could be captured by atomic nuclei without immediately being knocked free again. Electrons began to settle into orbits around protons, forming neutral hydrogen atoms. This process is called recombination, though it's a bit of a misnomer since the electrons and protons had never been combined before. It's sometimes also called the decoupling epoch, or the surface of last scattering. As electrons were captured into atoms, something important happened to the photons. Neutral atoms interact much more weakly with light than free electrons do. Once most of the electrons were bound, photons could suddenly travel freely through space without constantly scattering. The universe became transparent. The glowing fog lifted, and light could stream unimpeded across the cosmos. The photons that were released at this moment have been traveling through space ever since. As the universe expanded, these photons were stretched to longer wavelengths, shifting from visible light to infrared and eventually to microwaves. Today, we detect them as the cosmic microwave background, a faint glow of radiation coming from all directions with a temperature of just 2.7 degrees above absolute zero. This light is the oldest we can see, a direct view of the universe as it appeared 380,000 years after the Big Bang. The cosmic microwave background is a baby picture of the cosmos. The cosmic microwave background is our earliest snapshot. When we detect the cosmic microwave background, we're seeing light that has traveled for more than 13 billion years. It was emitted when the universe was less than 1/4000th of its current age, still in its infancy. This makes the CMB an incredibly powerful tool for understanding the early universe. By studying its properties, we can learn about conditions at that time in exquisite detail. The CMB appears almost perfectly uniform in all directions, with a temperature of about 2.725 Kelvin. But it's not perfectly smooth. There are tiny temperature variations, fluctuations of about 1 part in 100,000. These fluctuations are the most important feature of the CMB. They represent density variations in the early universe, regions that were slightly hotter and denser or slightly cooler and more diffuse. These tiny differences were the seeds from which all cosmic structure grew. The denser regions had slightly stronger gravity, which pulled in more matter over time. Over hundreds of millions of years, these small overdensities collapsed and grew, eventually forming the first stars, galaxies, and clusters of galaxies. The pattern of fluctuations in the CMB contains a wealth of information. By analyzing their sizes, shapes, and statistical properties, cosmologists can determine the universe's age, its composition, its geometry, and how fast it's expanding. The CMB has become the foundation of precision cosmology, allowing us to measure fundamental cosmic parameters to within a few % accuracy. It's remarkable that this ancient light, cooled and stretched by the expansion of space, still carries such clear information about the beginning of everything. The universe cooled rapidly as it expanded. As space stretched, everything inside it cooled. This isn't just a coincidence. It's a fundamental consequence of expansion. When a gas expands, it cools. The same thing happened to the entire universe. In the first fractions of a second, the temperature dropped from inconceivable heights down through ranges where different physical processes could occur. Each drop in temperature marked a transition, a moment when new structures could form or when certain interactions stopped being possible. From 10 to the 32 Kelvin at the Planck time, down to 10 billion Kelvin at 1 second, the universe cooled by a factor of 10 to the 21. From 10 billion degrees at 1 second down to 3,000 degrees at 380,000 years, it cooled by another factor of millions. And from 3,000 degrees at recombination down to the 2.7 Kelvin we measure today, it has cooled by roughly another factor of 1,000. This cooling will never stop. The universe will continue expanding forever, growing ever colder, ever more diffuse. In the unimaginably distant future, trillions upon trillions of years from now, the temperature will approach ever closer to absolute zero, though it will never quite reach it. The universe is slowly freezing, has been freezing since the moment it began, a long fade from infinite heat toward the ultimate cold of an eternally expanding cosmos. The neutron-to-proton ratio was locked in at 1 second. At 1 second after the Big Bang, something crucial happened. Before this moment, neutrons and protons were constantly converting into each other. A neutron could decay into a proton, releasing an electron and an antineutrino. A proton could capture an electron and become a neutron, releasing a neutrino. These reactions happened rapidly, keeping the numbers of neutrons and protons in equilibrium, balanced according to the temperature. But as the universe expanded and cooled, these reactions became less frequent. The weak force interactions that change neutrons into protons, and back require high energies or dense conditions. By 1 second after the Big Bang, the universe had expanded enough and cooled enough that these conversions essentially stopped. The ratio of neutrons to protons froze at whatever value it had reached. At that moment, there was about 1 neutron for every 5 or 6 protons. But neutrons are unstable. When free, not bound inside a nucleus, they decay with a half-life of about 10 minutes, transforming into protons. So, over the next several minutes, as the universe continued to expand and cool toward the conditions needed for nucleosynthesis, some of those neutrons decayed. By the time fusion began, around 3 minutes after the Big Bang, the ratio had shifted to about 1 neutron for every 7 protons. This might seem like an obscure detail, but it determined the composition of all ordinary matter in the universe. Almost every neutron that survived would end up locked inside a helium-4 nucleus. Since helium-4 contains 2 neutrons and 2 protons, the math works out such that about 1/8 of the protons also ended up in helium, with the rest remaining as hydrogen. This gives us the famous 75% hydrogen, 25% helium split. If the ratio had been different, the universe would have a different composition. If there had been more neutrons, there would be more helium. If there had been fewer, there would be less. The physics of the first second determined the makeup of all the atoms around you. Deuterium formed as the first step toward helium. When conditions became cool enough for nucleosynthesis, around 100 seconds after the Big Bang, the first nuclei to form were deuterium, also called heavy hydrogen. Deuterium is the simplest nucleus beyond a single proton. It contains one proton and one neutron bound together. But deuterium is fragile. Its binding energy is relatively low, which means it's easily destroyed by high-energy photons. In the very early universe, even when the temperature dropped low enough for deuterium to form, there were still so many energetic photons around that newly formed deuterium nuclei were immediately blasted apart. This created a bottleneck. Further fusion to helium requires deuterium as an intermediate step, but deuterium couldn't survive. Only when the universe cooled below about 900 million Kelvin and the number of highly energetic photons dropped sufficiently could deuterium begin to accumulate. This is sometimes called the deuterium bottleneck, and it delayed the onset of significant helium production. Once the bottleneck was passed, fusion proceeded rapidly. Deuterium nuclei fused with protons to form helium-3, 2 protons and 1 neutron. Helium-3 nuclei could then fuse with deuterium to form helium-4, or 2 helium-3 nuclei could fuse together to make helium-4 plus 2 protons. Helium-4 is very stable, one of the most tightly bound light nuclei, so once it formed, it stuck around. Within just a few minutes, nearly all available neutrons had been incorporated into helium-4 nuclei. A tiny amount of deuterium survived, about a few dozen parts per million, because the universe expanded and cooled so quickly that not quite all of it fused into helium. That leftover deuterium is still around today, and astronomers can measure its abundance in pristine gas clouds. The amount of deuterium left over is sensitive to the density of ordinary matter during nucleosynthesis, making it a powerful tool for measuring the baryon density of the universe. Helium-3 and lithium-7 were also produced in small amounts. While helium-4 was by far the most abundant product of Big Bang nucleosynthesis, small amounts of other light elements also formed. Helium-3, with 2 protons and 1 neutron, formed as an intermediate step in helium-4 production, and a small fraction survived without fusing further. Today, helium-3 exists at about 1 part per 100,000 compared to hydrogen. It's rare but detectable, and its abundance provides another check on Big Bang theory. Lithium-7, with 3 protons and 4 neutrons, also formed in tiny amounts, though the production process was more complex. Some formed through fusion of helium-4 and helium-3 nuclei. The predicted abundance is very small, about 1 part in 10 billion compared to hydrogen. Measuring primordial lithium has proven challenging. The oldest stars should show the primordial lithium abundance, but observations have found less lithium than predicted, a discrepancy called the lithium problem. It's not clear whether this represents a problem with Big Bang theory or with our understanding of how lithium is destroyed in stars. Most likely, it's the latter. Stars can burn lithium in their outer layers, reducing the observed abundance below the primordial value. Despite this puzzle, the overall picture remains clear. Big Bang nucleosynthesis produced hydrogen, helium-4, deuterium, helium-3, and lithium-7 in specific proportions that depend on just a few physical parameters. The agreement between predictions and observations for most of these elements is excellent, providing strong support for the Big Bang model and allowing us to measure fundamental properties of the early universe. No elements heavier than lithium formed. You might expect that fusion in the early universe would continue beyond helium and lithium, building up carbon, oxygen, and heavier elements through successive fusion reactions. After all, this is what happens in stars. But the early universe was different. The problem lies in nuclear physics. There are no stable nuclei with mass number 5 or 8. If you try to build beyond helium by adding one more proton or neutron, you get beryllium-5 or lithium-5, both of which decay almost instantly. If you try to fuse two helium-4 nuclei together, you get beryllium-8, which also falls apart almost immediately, splitting back into two helium nuclei. This is sometimes called the mass 5 and mass 8 gap. To get past it, you need the triple alpha process, where three helium-4 nuclei come together almost simultaneously to form carbon-12. But this requires special conditions. The density must be high enough, and the temperature must be in a narrow range, hot enough for the helium nuclei to overcome their electrical repulsion, but not so hot that newly formed carbon is immediately destroyed. Most importantly, these conditions must last long enough for the reaction to occur. In stars, particularly red giants, these conditions exist. The core is dense and hot, and it stays that way for thousands or millions of years, giving the triple alpha process time to build up carbon. But in the early universe, the density was dropping rapidly as space expanded. By the time the temperature had dropped to where triple alpha fusion could occur, the density was already too low. The universe expanded too quickly. The window for nucleosynthesis closed after just about 20 minutes, with the universe consisting of hydrogen, helium, and traces of deuterium and lithium. All heavier elements would have to wait for stars. This is a profound realization. Every carbon atom in your body, every oxygen molecule you breathe, every calcium atom in your bones, every iron atom in your blood, all of them were forged in stars, not in the Big Bang. We are literally made of stardust, the ashes of long-dead stars scattered through space and gathered into new worlds. The universe entered the photon-dominated era. After nucleosynthesis ended, around 20 minutes after the Big Bang, the universe entered a long period where photons carried most of the energy. Matter existed as nuclei and free electrons, but the energy density was dominated by radiation. This is called the radiation-dominated era, and it lasted for tens of thousands of years. During this time, matter and radiation were tightly coupled through Thomson scattering. Photons constantly collided with free electrons, and electrons constantly absorbed and re-emitted photons. This kept matter and radiation at the same temperature and prevented photons from traveling freely. The universe was filled with a hot, opaque plasma. The pressure from radiation was strong enough to resist gravitational collapse, preventing matter from clumping together to form structures. Density fluctuations existed, tiny variations from place to place in how much matter there was, but they couldn't grow. Gravity tried to pull over dense regions together, but radiation pressure pushed back. This created oscillations, regions of compression and rarefaction, like sound waves propagating through the primordial plasma. These are called baryon acoustic oscillations, and they left an imprint on the matter distribution and on the cosmic microwave background that we can still detect today. As the universe continued to expand and cool, the energy density of radiation dropped faster than the energy density of matter. Radiation energy density decreases as the fourth power of the scale factor, while matter energy density decreases as the third power. Eventually, around 50,000 years after the Big Bang, the energy density of matter overtook that of radiation, and the universe transitioned from being radiation-dominated to matter-dominated. This transition allowed gravitational collapse to begin in earnest. Overdense regions, especially those of dark matter which wasn't affected by radiation pressure, began to collapse more efficiently, forming the seeds of future galaxies. The cosmic microwave background was released at recombination. Around 380,000 years after the Big Bang, the universe had cooled to about 3,000 Kelvin. At this temperature, electrons could finally be captured by atomic nuclei without immediately being knocked free again. Hydrogen nuclei, single protons, grabbed electrons to form neutral hydrogen atoms. Helium nuclei captured their electrons to become neutral helium. This process is called recombination, and it fundamentally changed the universe. Before recombination, photons could not travel freely. They constantly scattered off free electrons, bouncing from one to another like light trying to shine through fog. But once electrons were bound into atoms, neutral atoms interact much more weakly with photons. Suddenly, the photons that filled the universe could stream freely through space without scattering. The universe became transparent. This moment defines the surface of last scattering. The photons that last scattered off electrons just before recombination are the ones we see today as the cosmic microwave background. They have been traveling through space ever since, stretched by the expansion of the universe from visible and infrared light into microwaves. When we look at the CMB, we're seeing the universe as it appeared at the moment of recombination, a direct view of the cosmos when it was just 380,000 years old. Every direction we look, we see light from that moment, forming a spherical shell around us in time. This shell is as far back as we can see with light. Before recombination, the universe was opaque. The CMB is our ultimate horizon, the farthest edge of the observable universe in time. It's like a glowing wall surrounding us, beyond which no light from earlier times can reach us. The surface of last scattering contains incredible information. Tiny temperature variations in the CMB, just millionths of a degree, reveal density fluctuations in the early universe. These fluctuations show where matter was slightly more or less dense. The patterns tell us about the physics of the early universe, about sound waves propagating through the plasma, about the geometry of space, about the types and amounts of matter and energy present. The CMB is the most important observational pillar of modern cosmology. Penzias and Wilson discovered the CMB by accident. In 1964, two scientists at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were trying to eliminate noise from a radio antenna designed for satellite communications. No matter what they did, they couldn't get rid of a persistent background hiss. They checked their equipment meticulously, even removing pigeons nesting in the antenna and cleaning out what they delicately termed a white dielectric material. But the noise remained. It came from all directions, didn't vary with time of day or season, and had a constant strength. Meanwhile, just down the road at Princeton University, a team of cosmologists led by Robert Dick had been planning to search for the cosmic microwave background, predicted decades earlier by George Gamow and his colleagues. When Dick heard about the unexplained noise in the Bell Labs antenna, he realized immediately what it was. Penzias and Wilson had accidentally discovered the CMB, the afterglow of the Big Bang itself. The noise they detected had a temperature of about 3 Kelvin and came uniformly from the entire sky, exactly as predicted. This discovery provided the most direct evidence for the Big Bang theory and transformed cosmology from a largely speculative field into an observational science. Penzias and Wilson received the Nobel Prize in Physics in 1978 for their discovery. It's one of the great examples of serendipity in science, a world-changing discovery made while trying to eliminate an annoying technical problem. The CMB was predicted before it was discovered, a triumph of theoretical physics confirmed by observation. The CMB temperature is incredibly uniform. One of the most striking features of the cosmic microwave background is its uniformity. When you measure its temperature in different directions, you find that it's almost exactly the same everywhere, about 2.725 Kelvin. The variation from place to place is tiny, only about 1 part in 100,000. This level of uniformity was initially puzzling. It implies that the early universe was extraordinarily smooth and homogeneous. Regions of space that are now on opposite sides of the observable universe, so far apart that light hasn't had time to travel between them since the Big Bang, nonetheless have almost exactly the same temperature. How did they know to have the same temperature if they were never in contact? This is the horizon problem, one of the key puzzles that inflation was designed to solve. Before inflation, all of the observable universe was compressed into a tiny region, small enough that light could cross it many times, allowing temperature to equalize. Then, inflation stretched this small uniform patch to enormous size, far larger than the currently observable universe. The uniformity we see today is the stretched-out remnant of that early equilibrium. Despite the overall uniformity, tiny variations exist. These anisotropies in the CMB temperature, measured at the level of about 50 microkelvins, are the most important feature of the CMB. They represent density fluctuations in the early universe, regions that were slightly hotter and denser, or slightly cooler and more rarefied. Without these fluctuations, the universe would have remained perfectly smooth forever. No galaxies, no stars, no planets, no life would have formed. Gravity needs something to work with, some initial lumpiness to amplify. The CMB fluctuations provided that lumpiness, the seeds from which all cosmic structure grew. Tiny fluctuations in the CMB show where galaxies would form. The temperature variations in the cosmic microwave background aren't random noise. They have structure and pattern, and that structure tells a story. The slightly hotter regions in the CMB correspond to places where matter was slightly denser. These overdense regions had stronger gravity, which pulled in more matter over time, while underdense regions lost matter to their surroundings. Over hundreds of millions of years, these small differences grew. Gravity amplified the initial fluctuations. Dense regions became denser, their gravity pulling in more and more matter. Eventually, these regions collapsed into the first stars and galaxies. If you could map the density fluctuations in the early universe shown by the CMB, and then fast forward billions of years, you would see galaxies forming preferentially in the regions that started out slightly overdense. The large-scale structure of the universe today, the distribution of galaxies in clusters, superclusters, and vast filaments, can be traced back to these primordial fluctuations. Astronomers have confirmed this by comparing the pattern of fluctuations in the CMB with the distribution of galaxies today. They match. The same statistical patterns appear at both epochs, stretched and amplified by billions of years of gravitational growth. This is powerful evidence that we understand cosmic structure formation. The tiny ripples in the CMB, just 1 part in 100,000, have grown into the rich cosmic web of galaxies we see today. In a very real sense, the CMB shows us a map of the universe's destiny, the blueprint from which everything would be built. The fluctuations originated from quantum uncertainty during inflation. Where did the fluctuations in the CMB come from? Why wasn't the early universe perfectly smooth? The answer takes us back to the first moments, to inflation and quantum mechanics. During inflation, the universe was governed by quantum physics. At the quantum level, nothing is perfectly certain or smooth. There are always fluctuations, random variations driven by the Heisenberg uncertainty principle. In normal circumstances, these quantum fluctuations are tiny and fleeting, affecting only microscopic scales. But during inflation, something remarkable happened. The exponentially rapid expansion of space stretched these tiny quantum fluctuations up to enormous sizes. Fluctuations that started out smaller than a proton were blown up to sizes larger than galaxies, larger even than the observable universe. These stretched quantum fluctuations became frozen into the fabric of space as classical density perturbations. They were no longer quantum mechanical, but had become real variations in the density of matter and energy. When inflation ended, these fluctuations remained, imprinted on the distribution of matter and radiation. They're the reason the CMB isn't perfectly smooth. They're the seeds of all cosmic structure. This is one of the most profound ideas in cosmology. The largest structures in the universe, galaxy clusters spanning hundreds of millions of light years, originated from quantum fluctuations, from the inherent uncertainty built into nature at the smallest scales. Inflation took the microscopic and made it cosmic. The pattern of these fluctuations depends on the physics of inflation, on how fast the expansion occurred, how long it lasted, and what drove it. By measuring the detailed properties of CMB fluctuations, cosmologists can test different models of inflation and constrain what happened in the first tiny fraction of a second after the Big Bang. It's remarkable that we can study events that occurred 10 to the negative 35 seconds after creation by looking at light that has traveled for nearly 14 billion years. The COBE satellite first mapped the CMB fluctuations. For decades after the discovery of the cosmic microwave background, astronomers knew it existed and had measured its average temperature precisely. But detecting the tiny fluctuations, the variations from place to place, required much more sensitive instruments. Ground-based and balloon-borne experiments searched for these variations throughout the 1970s and 80s with limited success. The fluctuations were just too small. Then, in 1989, NASA launched the Cosmic Background Explorer, or COBE, satellite. COBE carried instruments specifically designed to measure the CMB with unprecedented precision. In 1992, the COBE team announced a landmark discovery. They had detected fluctuations in the CMB temperature at the level of about 30 microkelvins, 1 part in 100,000, exactly as predicted. The announcement made front-page news. Scientists called it "seeing the face of God," a glimpse of the universe in its infancy. The COBE data showed that the fluctuations had specific statistical properties consistent with predictions from inflation. They appeared to be the same strength at all scales measured, forming what's called a scale invariant or Harrison-Zeldovich spectrum, exactly what simple models of inflation predicted. This discovery opened the era of precision cosmology. For the first time, cosmologists had detailed data about the early universe that could be used to test theories and measure cosmic parameters. John Mather and George Smoot, leaders of the COBE project, received the Nobel Prize in Physics in 2006 for this work. COBE's measurements were just the beginning. Subsequent experiments would map the fluctuations in far greater detail. The WMAP mission refined our view dramatically. While COBE detected the CMB fluctuations, its resolution was limited. It could only distinguish features larger than about 7 degrees on the sky, roughly 14 times the width of the full moon. To learn more, astronomers needed to map the fluctuations on smaller scales. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, or WMAP, named after cosmologist David Wilkinson. WMAP orbited the Sun at a special location called the L2 Lagrange point, about 1 million miles from Earth, where it had a clear view of the entire sky unobstructed by Earth's radiation. Over 9 years, WMAP measured the CMB temperature across the entire sky with a resolution about 30 times better than COBE. The results were stunning. WMAP produced detailed maps showing the fluctuations in exquisite detail, revealing patterns and features that contained a wealth of information. The data allowed cosmologists to measure fundamental cosmic parameters with precision previously unimaginable. WMAP determined that the universe is 13.77 billion years old, give or take about 60 million years. It measured the density of ordinary matter, and dark energy. It determined that the geometry of space is flat, or very nearly so. It confirmed that the fluctuations originated during inflation. The WMAP data also revealed several peaks and troughs in the power spectrum of fluctuations, the statistical description of how strong fluctuations are at different angular sizes. These peaks correspond to sound waves in the primordial plasma, acoustic oscillations that compressed and rarefied matter before recombination. The positions and heights of these peaks depend sensitively on the universe's composition and geometry. The fact that observations matched theoretical predictions so precisely confirmed the standard cosmological model called lambda CDM, where lambda represents dark energy and CDM stands for cold dark matter. WMAP transformed cosmology from a field where parameters were uncertain by factors of 2 or more into a precision science where we know key numbers to a few percent. The Planck satellite gave us the sharpest view yet. In 2009, the European Space Agency launched the Planck satellite, named after physicist Max Planck. Like WMAP, Planck orbited at the L2 point and mapped the entire sky in microwaves. But Planck had significantly better resolution and sensitivity. It could distinguish features less than 5 arc-minutes across, about 1/6 the width of the Moon, and could measure temperature differences as small as a few microkelvins. Planck operated for about 4 years and produced the most detailed map of the cosmic microwave background ever made. The image is iconic, an oval map of the sky painted in false colors showing the tiny temperature variations across the heavens. It looks mottled, with warm and cool spots distributed in a complex pattern that encodes the quantum fluctuations from inflation, the acoustic oscillations of the primordial plasma, and the large-scale geometry of spacetime. Analysis of Planck data refined the measurements, from WMAP even further. Planck determined the universe's age to be 13.797 billion years, with an uncertainty of less than 0.5%. It measured the Hubble constant, the current expansion rate of the universe, though this measurement has led to some tension with other methods. It determined that ordinary matter makes up 4.9% of the universe's total energy density, dark matter makes up 26.8%, and dark energy makes up 68.3%. These numbers define the standard cosmological model. Planck also tested the predictions of inflation more stringently than ever before, confirming that the fluctuations are nearly but not exactly scale invariant, with slightly less power at large scales, as predicted by many inflation models. The Planck data placed tight constraints on the number of neutrino species, the amount of primordial helium, and many other parameters. It's remarkable how much information is encoded in the pattern of temperature fluctuations in ancient light. The cosmic microwave background has become the foundation of our understanding of the universe. Acoustic peaks reveal the universe's composition. One of the most important features in the cosmic microwave background is a series of peaks and troughs in the fluctuation power spectrum. These acoustic peaks aren't visible in the sky map itself, but appear when you analyze the statistics of the fluctuations, measuring how much variation exists at different angular scales. The peaks represent sound waves in the primordial plasma before recombination. In the early universe, regions of higher density had stronger gravity, pulling matter inward. But the radiation pressure resisted this collapse, pushing outward. This created oscillations, with matter and radiation sloshing back and forth like sound waves. Some regions were at maximum compression when recombination occurred. These show up as the first acoustic peak, corresponding to fluctuations about 1 degree across on the sky. Other regions were at maximum rarefaction or at intermediate phases, producing subsequent peaks at smaller angular scales. The positions of these peaks depend on several factors, including the curvature of space, the density of matter, and the relative amounts of ordinary matter and dark matter. Ordinary matter, which interacts with radiation, behaves differently from dark matter, which doesn't. This affects the heights of the odd-numbered and even-numbered peaks differently. By measuring the precise positions and heights of multiple peaks, cosmologists can determine the universe's composition with remarkable accuracy. The first peak tells us the universe is geometrically flat. The relative heights of the peaks tell us how much ordinary matter versus dark matter exists. The damping of the peaks at small scales tells us about conditions at recombination. It's extraordinary that sound waves from the first few 100,000 years of cosmic history have left such clear signatures that we can read them billions of years later. These acoustic peaks are among the strongest evidence we have for dark matter and dark energy, and they precisely constrain the universe's fundamental parameters. The universe was once just 3,000 degrees. At the time of recombination, when the cosmic microwave background was released, the universe had a temperature of about 3,000 Kelvin. That's about half the temperature of the sun's surface. If you could have been there, the entire sky would have glowed with a reddish-orange light, similar to the glow of heated metal. There would be no stars, no galaxies, nothing but a uniform glow from every direction. As space expanded, this light was stretched to longer wavelengths and cooled. Today, that 3,000-degree glow has been redshifted into microwaves with a temperature of just 2.7 Kelvin, barely above absolute zero. The ratio tells us how much the universe has expanded. The CMB has cooled by a factor of about 1100, which means the universe has expanded by a factor of about 1100 since recombination. Distances between distant objects are now 1100 times larger than they were when the CMB was emitted. This redshift, often denoted Z, is about 1090. We can see this stretching directly. The wavelength of CMB photons has been stretched by the same factor. What was once visible light, around 500 nanometers, is now microwave radiation with wavelengths around half a millimeter. This stretching of light by cosmic expansion is called cosmological redshift, and it's one of the most direct pieces of evidence that the universe is expanding. Every photon in the CMB carries information about the expansion history of the universe encoded in its wavelength. The cosmic microwave background is nearly perfect blackbody radiation. When physicists study the spectrum of the cosmic microwave background, measuring how much energy it contains at each wavelength, they find something remarkable. The CMB has an almost perfect blackbody spectrum, the characteristic curve of thermal radiation emitted by an object in perfect thermal equilibrium. This was first measured precisely by the COBE satellite's FIRIS instrument, which found that the CMB spectrum matches a blackbody curve more perfectly than any other blackbody ever measured, natural or artificial. The match is so precise that if you plotted the theoretical curve and the measured data points on a graph, you couldn't see any difference. They would lie exactly on top of each other. This perfect blackbody spectrum tells us that the early universe was in thermal equilibrium. Matter and radiation had the same temperature, and they had enough time to exchange energy and reach a balanced state. This supports the picture of a hot, dense early universe, where everything was in contact, where conditions were uniform. If the Big Bang model were wrong, if the CMB came from some other source, it would be extraordinarily unlikely to have such a perfect blackbody spectrum. Stars don't produce perfect blackbodies. Neither do gas clouds or any other astrophysical sources. Only a system in perfect thermal equilibrium does, and only the early universe provides the conditions for that. The tiny deviations from perfection that do exist are themselves informative. At very high frequencies, there are slight distortions caused by the scattering of CMB photons off hot gas in galaxy clusters, an effect called the Sunyaev-Zeldovich effect. These distortions are used to study the distribution of hot gas and dark matter in the universe. But these are secondary effects, alterations that occurred long after the CMB was created. The primordial spectrum remains perfectly thermal, a relic of the universe's hot, dense beginning. We can only see so far back with light. The cosmic microwave background represents a fundamental horizon in observational cosmology. It's the farthest back in time we can see using electromagnetic radiation. Before recombination, the universe was opaque. Photons couldn't travel freely because they constantly scattered off free electrons. Any light from earlier times has been effectively erased, absorbed, and re-emitted so many times that no information survives about its origin. This means we cannot use light to directly observe the universe before 380,000 years after the Big Bang. Everything earlier than that is hidden behind the opaque veil of the photon epoch. It's like trying to see inside a fog. The CMB is the fog itself, and we cannot see through it. This doesn't mean we know nothing about earlier times. We can infer conditions through physics, through the products of earlier processes like Big Bang nucleosynthesis, and through effects imprinted on the CMB itself. The patterns in the CMB tell us about events that occurred earlier, during inflation, and immediately after. But we cannot directly see those events with light. To probe earlier times, we need particles that decoupled sooner than photons. Neutrinos decoupled at 1 second, so a cosmic neutrino background exists that could tell us about the universe at that age, though we haven't yet detected it. Gravitational waves can travel freely through matter and radiation, so they could carry information from even earlier times, perhaps from inflation itself. Detecting primordial gravitational waves is one of the holy grails of cosmology. They would open a window into the first moments after the Big Bang, allowing us to see what happened when the universe was far younger than we can observe with light. The CMB is our earliest light, but it's not the end of the story. Other messengers from even deeper in the past may yet reveal themselves. Primordial element abundances confirm the Big Bang. The second major pillar of Big Bang cosmology, after the cosmic microwave background, is the abundance of light elements. The theory of Big Bang nucleosynthesis makes precise predictions about how much hydrogen, helium, deuterium, and lithium should exist in the universe, based on the physics of the first few minutes. These predictions depend on just a few parameters, particularly the density of ordinary matter and the expansion rate during nucleosynthesis. When astronomers measure the primordial abundances, looking at the oldest stars and the most pristine gas clouds, they find remarkable agreement with predictions. Hydrogen makes up about 75% of ordinary matter by mass. Helium-4 makes up about 25%, just as predicted. Deuterium exists at a level of about 2 to 3 parts in 100,000 relative to hydrogen. Helium-3 exists at about 1 part in 100,000. Lithium-7 exists at about 1 part in 10 billion, though, as mentioned earlier, there's some tension between predictions and observations for lithium. The agreement for hydrogen, helium, and deuterium is stunning. No other theory explains these abundances. They're not produced by stars in these proportions. Stars make helium from hydrogen, but they make much less than 25%, and they make it continuously over billions of years, not all at once. Stars also destroy deuterium rather than creating it. The only way to explain why the universe has these particular abundances is through the physics of the hot, dense, rapidly expanding early universe. Furthermore, the abundances are consistent across the entire universe. Whether we look at gas clouds in our galaxy or in distant galaxies billions of light years away, we find the same primordial composition. This uniformity confirms that nucleosynthesis occurred everywhere at the same time, during a universal, hot, dense phase. The match between theory and observation is one of the great triumphs of 20th century physics. George Gamow, Ralph Alpher, and Robert Herman predicted in the 1940s that the Big Bang should produce helium and should leave behind a cosmic radiation background. Both predictions were confirmed decades later. Their work, though not fully appreciated at the time, laid the foundation for modern cosmology. Helium abundance constrains the early universe. The amount of helium-4 produced during Big Bang nucleosynthesis is particularly important because it's sensitive to conditions in the first few minutes. The helium abundance depends primarily on two things: the neutron-to-proton ratio when nucleosynthesis began, and the expansion rate of the universe at that time. The neutron-to-proton ratio was determined by the balance between weak interactions that convert neutrons to protons and vice versa, and by neutron decay during the first few minutes. This ratio depends on fundamental constants of physics. The expansion rate, in turn, depends on the total energy density of the universe at that time, which includes contributions from ordinary matter, photons, and neutrinos. If the expansion were faster, nucleosynthesis would happen earlier when the neutron-to-proton ratio was higher, leading to more helium. If the expansion were slower, more neutrons would decay before nucleosynthesis, leading to less helium. By measuring the primordial helium abundance very precisely, cosmologists can constrain the expansion rate during nucleosynthesis. This provides an independent check on the standard model of particle physics. For instance, the helium abundance is sensitive to the number of neutrino species. Additional types of neutrinos would contribute more energy density, speeding up expansion and increasing helium production. The observed helium abundance is consistent with exactly 3 species of light neutrinos, in perfect agreement with particle physics experiments. This is a beautiful example of how cosmology and particle physics connect. The universe in its first 3 minutes serves as a laboratory for testing fundamental physics at energies we cannot achieve in any accelerator. The early universe was hotter and denser than anything in the present cosmos, and the remnants of that era, the light elements, carry information about physics at those extreme conditions. Deuterium is especially sensitive to baryon density. Of all the light elements, deuterium is the most sensitive probe of the density of ordinary matter, or baryons, during Big Bang nucleosynthesis. Deuterium is fragile. It's easily destroyed in stars, where it burns at lower temperatures than hydrogen. This means that stars reduce the amount of deuterium over time, but they don't create it. The deuterium we observe today is all primordial, left over from the Big Bang, minus whatever has been destroyed in stars. The amount of primordial deuterium produced depends strongly on the baryon density. If there's more ordinary matter, collisions between particles are more frequent, and more deuterium gets converted into helium during nucleosynthesis. If there's less ordinary matter, collisions are rarer and more deuterium survives. This makes deuterium an excellent barometer for the density of ordinary matter in the early universe. Astronomers measure primordial deuterium by observing distant quasars. Light from these bright distant objects passes through intervening gas clouds on its way to Earth. By analyzing the absorption lines in the quasar spectra, astronomers can determine the chemical composition of these clouds, including their deuterium content. The most pristine clouds, those that have never been part of stars, show the primordial deuterium abundance. Current measurements indicate a primordial deuterium to hydrogen ratio of about 2.5 parts in 100,000. This measurement, combined with Big Bang nucleosynthesis theory, tells us the density of ordinary matter in the universe. The result agrees beautifully with completely independent measurements from the cosmic microwave background. Both methods give a baryon density of about 4 to 5% of the critical density, the density needed to make the universe flat. This agreement between 2 completely different methods, one based on nuclear physics in the first 3 minutes, and the other based on photon physics at 380,000 years, is powerful confirmation that we understand the early universe. The puzzle of lithium-7 remains unsolved. While the predictions for hydrogen, helium-4, and deuterium match observations very well, there's a persistent discrepancy with lithium-7. Big Bang nucleosynthesis predicts a primordial lithium abundance of about 5 parts in 10 billion relative to hydrogen. But when astronomers measure lithium in the oldest, most metal-poor stars, they find only about 1 to 2 parts in 10 billion, a factor of 2 to 3 less than predicted. This is called the lithium problem, and it's been known for decades without a clear resolution. Several explanations have been proposed. Perhaps lithium is destroyed in the outer layers of stars more efficiently than we thought, reducing the observed abundance below the primordial value. Stars can burn lithium at relatively low temperatures, and mixing processes might bring surface material down into hotter regions where it's destroyed. Another possibility is that our measurements are incomplete or biased. Perhaps we're not observing stars that truly show the primordial abundance. Or perhaps there's something wrong with how we measure lithium in stellar atmospheres. A more radical possibility is that there's new physics affecting Big Bang nucleosynthesis. Perhaps the universe expanded at a different rate than we think, or perhaps there are additional particles or forces we don't know about. But this seems unlikely because the predictions for all the other elements work so well. Most physicists suspect the answer lies in stellar astrophysics, rather than in the physics of the Big Bang. But until the discrepancy is resolved, the lithium problem remains a small but intriguing puzzle. It's a reminder that even in our best confirmed theories, there are loose ends and details we don't fully understand. Science progresses not just by confirming predictions, but by investigating anomalies, the places where theory and observation don't quite match. No alternative theory matches all the evidence. Over the decades since the Big Bang theory was first proposed, various alternative theories have been suggested. The most prominent was the steady-state theory, championed by Fred Hoyle, Hermann Bondi, and Thomas Gold in the 1940s and 50s. This theory proposed that the universe has always existed in roughly its current form, with no beginning. As the universe expands, new matter is continuously created to maintain a constant density. For a time, this was a viable competitor to the Big Bang, but observations gradually ruled it out. The discovery of the cosmic microwave background in 1964 was the death knell for steady state. The theory had no natural explanation for why the universe should be filled with thermal radiation at 2.7 Kelvin. Big Bang theory predicted it. Steady state did not. The primordial element abundances also favor the Big Bang. Steady state theory requires that all elements be made in stars, but stars don't produce helium in the observed proportions, and they destroy rather than create deuterium. Other alternative theories have been proposed over the years. Some invoke exotic physics, new forces, or modifications to gravity. But none match the breadth of evidence that supports the standard Big Bang cosmology. The CMB, the element abundances, the expansion of the universe, the age and evolution of galaxies. All of these fit together in the Big Bang framework. Alternative theories might explain one or two observations but fail to account for the full picture. This doesn't mean the Big Bang theory is complete or perfect. There are open questions, mysteries about dark matter and dark energy, puzzles about the very earliest moments, but the basic framework that the universe began in a hot, dense state and has been expanding and cooling ever since is supported by overwhelming evidence from multiple independent lines of observation. It's as well established as any theory in science. Hubble's discovery revealed the expanding universe. The first hint that the universe had a beginning came not from theoretical physics, but from astronomical observations. In the 1920s, astronomer Edwin Hubble, working at the Mount Wilson Observatory in California, was studying galaxies. Using the powerful 100-inch telescope, the largest in the world at the time, he measured the distances to nearby galaxies and their speeds. What he found was revolutionary. Galaxies were moving away from us, and the farther away they were, the faster they were receding. This relationship, now called Hubble's law, implies that the universe is expanding. If galaxies are moving apart now, they must have been closer together in the past. If you run the expansion backward, you reach a point where everything was in the same place, a moment of infinite density and temperature, the beginning. This was not what most scientists expected. Albert Einstein had formulated his theory of general relativity in 1915, which describes gravity and the structure of space-time. When Einstein applied his equations to the universe as a whole, he found that they predicted either an expanding or contracting universe. This troubled him. He believed, like most people at the time, that the universe was static and eternal. So he added an extra term to his equations, the cosmological constant, to hold the universe still, balancing gravity's inward pull with an outward repulsion. When Hubble's observations were announced in 1929, Einstein realized his mistake. The universe was indeed expanding. He later called the cosmological constant his greatest blunder. Ironically, we now know that something like the cosmological constant does exist, in the form of dark energy, but it's not holding the universe still. It's accelerating the expansion. Hubble's discovery transformed our understanding of the cosmos. The universe has a history. It changes over time, and if it's expanding now, it must have been denser and hotter in the past, leading inevitably to the concept of a beginning, the Big Bang. Redshift measures cosmic expansion. Hubble measured the speeds of galaxies using a phenomenon called redshift. When a source of light is moving away from you, the wavelengths of the light are stretched, shifted toward the red end of the spectrum. This is similar to the Doppler effect for sound, where a siren's pitch drops as an ambulance drives away. For nearby galaxies, redshift is caused by their motion through space. But for distant galaxies, something more profound happens. The redshift is caused by the expansion of space itself. As space stretches, it carries the galaxies with it, and it also stretches the light traveling through it. A photon emitted billions of years ago has had its wavelength stretched by the expansion of the universe that occurred while it was traveling. The amount of stretch tells us how much the universe has expanded since the light was emitted. Astronomers measure redshift by looking at spectral lines, specific wavelengths of light absorbed or emitted by atoms. Each element produces a unique pattern of lines, like a fingerprint. In distant galaxies, these patterns appear shifted toward longer wavelengths compared to their rest wavelengths measured in laboratories. The redshift, denoted by the letter Z, is defined as the fractional change in wavelength. A redshift of Z equals 1 means wavelengths have doubled, so the universe has expanded by a factor of 2 since that light was emitted. A redshift of Z equals 2 means a factor of 3 expansion, and so on. The most distant galaxies we've observed have redshifts around Z equals 10 to 14, meaning the universe has expanded by a factor of 11 to 15 since those galaxies emitted their light. The cosmic microwave background has a redshift of about Z equals 1090, reflecting the enormous expansion since recombination. Redshift is one of the most powerful tools in cosmology, allowing us to measure distances, ages, and the expansion history of the universe. The universe's expansion is accelerating. In the late 1990s, 2 teams of astronomers were studying distant supernovae, stellar explosions that can be used as standard candles to measure cosmic distances. They expected to find that the universe's expansion was slowing down over time, decelerated by the gravitational pull of matter. Instead, they found the opposite. The expansion is speeding up. Distant supernovae appeared fainter than expected, meaning they were farther away than they should be if the universe were decelerating. The only way to explain this was if the expansion rate had increased over time, if something was pushing the universe apart, overcoming gravity. This discovery, announced in 1998, was shocking. It earned the leaders of the two teams, Saul Perlmutter, Brian Schmidt, and Adam Rouse, the Nobel Prize in Physics in 2011. The cause of this acceleration is called dark energy, and it remains one of the deepest mysteries in physics. Dark energy appears to be a property of space itself, a kind of energy inherent in the vacuum. As the universe expands, more space is created, and with it, more dark energy. This pushes galaxies apart faster and faster. Dark energy makes up about 68% of the total energy density of the universe, far more than ordinary matter or even dark matter. Its nature is unknown. It might be Einstein's cosmological constant, a fixed energy density of empty space. Or it might be something more dynamic, a field that changes over time. Understanding dark energy is one of the central challenges of modern cosmology. It determines the fate of the universe. If dark energy remains constant, the universe will expand forever, faster and faster, eventually tearing apart all structures in what's called the Big Rip. If dark energy weakens, expansion might slow. If it becomes repulsive enough, it could reverse. We don't know. What we do know is that the universe's expansion history is more complex than we thought, and that the cosmos is being driven apart by something we barely understand. The early universe was incredibly dense. When we run the expansion backward, compressing the universe toward its beginning, densities become unimaginably large. At 1 second after the Big Bang, the density of the universe was about 4 billion kilograms per cubic meter, roughly 4 million times denser than water, comparable to the density inside an atomic nucleus. At 1 microsecond, 10 to the negative 6 seconds, the density was even higher, about 10 to the 18 kilograms per cubic meter, with all of space filled with quark-gluon plasma. At the Planck time, 10 to the negative 43 seconds, if our physics even applies there, the density would have been about 10 to the 94 kilograms per cubic meter. These numbers are almost meaningless because they're so far beyond everyday experience. But they illustrate the extreme conditions of the early universe. Matter and energy were compressed to densities where normal structures couldn't exist. Atoms, nuclei, even protons and neutrons were broken apart into their constituent particles. As the universe expanded, this density dropped rapidly. By the time of recombination, 380,000 years after the Big Bang, the density had fallen to about 10 to the negative 18 kilograms per cubic meter. Far more diffuse than any vacuum we can create on Earth, but still much denser than today. Now, the average density of matter in the universe is about 10 to the negative 27 kilograms per cubic meter, equivalent to about 6 hydrogen atoms per cubic meter of space. That's extraordinarily diffuse, emptier than the best laboratory vacuums. Yet, even this tiny density, spread across the vast volume of the universe, adds up to an enormous total mass. The observable universe contains on the order of 10 to the 80 atoms, a number so large it defies comprehension. All of them emerged from the hot, dense state of the Big Bang, spread thin by cosmic expansion. The horizon distance defines what we can see. Because the universe has a finite age and light travels at a finite speed, there's a limit to how far we can see. Light from regions beyond a certain distance hasn't had time to reach us yet. This defines the observable universe, the region of space from which light has had time to travel to us since the Big Bang. You might think the observable universe has a radius of 13.8 billion light-years, equal to the age of the universe times the speed of light. but it's actually much larger because the universe has been expanding while light was traveling. Light emitted shortly after the Big Bang from a galaxy that was initially close to us has been traveling for nearly 13.8 billion years. But meanwhile, that galaxy has been carried away by cosmic expansion. Today, that galaxy is about 46 billion light-years away. This means the observable universe has a radius of about 46 billion light-years, or a diameter of about 93 billion light-years. This is called the particle horizon, the distance to the farthest regions from which light has had time to reach us. Beyond this horizon, the universe continues, but we cannot see it. We don't know how much larger the full universe is beyond what we observe. It might be just slightly larger, or it might be infinite. If inflation occurred, the universe is likely vastly larger than the observable region, perhaps infinite. We can only observe our cosmic neighborhood, a sphere centered on Earth, bounded by the finite speed of light and the finite age of the universe. As time passes, the observable universe grows. Light from more distant regions reaches us, revealing previously hidden galaxies. But paradoxically, because of accelerating expansion, there are galaxies we can see now that we will eventually lose contact with. They're being carried away faster than light can travel through the expanding space between us. In the far future, most galaxies will disappear beyond our horizon, leaving future observers in a lonelier cosmos. The CMB shows us the universe at 0.003% of its current age. When we observe the cosmic microwave background, we're looking at light that has traveled for over 13 billion years. This light was emitted when the universe was just 380,000 years old. To put this in perspective, if the current age of the universe, 13.8 billion years, were compressed into a single year, the CMB would show us the universe as it appeared about 18 minutes after midnight on January 1st. It's an incredibly early snapshot. Everything that has happened since, the formation of the first stars, the assembly of galaxies, the birth of planets, the emergence of life, all of that occurred in the remaining 364 days and 23 hours and 42 minutes. We are seeing the universe at less than 3/1000% of its current age. This makes the CMB our earliest direct observation of the cosmos. It's the baby picture of the universe, showing conditions before stars, before structure, before almost anything recognizable. The patterns in the CMB are the seeds from which everything grew. By studying them, we're watching the beginning of the process that would eventually lead to galaxies, stars, planets, and ultimately to us. It's humbling to realize that all the complexity around us, all the structure and diversity, emerged from such simple, uniform beginnings. The early universe was almost perfectly smooth, with variations of only 1 part in 100,000. Yet those tiny variations, amplified by billions of years of gravitational growth, became the cosmic web of galaxies we observe today. Everything traces back to those earliest moments, to quantum fluctuations during inflation, to the physics of the first second, to the formation of light elements in the first 3 minutes, and to the release of the cosmic microwave background at 380,000 years. Each era left its mark, and we can read those marks today, interpreting the ancient light and the chemical abundances like archaeologists studying artifacts from a lost civilization. The Dark Ages followed recombination. After the cosmic microwave background was released and the universe became transparent, you might expect that we could observe what happened next. But there's a gap in our observations. After recombination, the universe entered a period called the Dark Ages, a time when no sources of light existed. The CMB was fading and redshifting into the infrared and beyond. The first stars had not yet formed. The universe was filled with neutral hydrogen and helium gas, dark and cold, gradually cooling as it expanded. This period lasted for perhaps 100 million years, maybe longer. During this time, gravity was at work. The density fluctuations imprinted during inflation and visible in the CMB were growing. Regions that were slightly overdense pulled in more matter. Dark matter, which doesn't interact with radiation, could collapse more easily than ordinary matter. Dark matter began to form halos, gravitational wells where matter accumulated. Ordinary matter, the hydrogen and helium gas, fell into these dark matter halos, gathering in clouds that grew denser and denser. Eventually, in the densest regions, gas clouds became so compressed that temperatures and pressures rose high enough for nuclear fusion to ignite. The first stars were born. This moment, sometime between 100 and 200 million years after the Big Bang, marked the end of the Dark Ages and the beginning of the cosmic dawn. These first stars were very different from the Sun. They formed from pure hydrogen and helium with no heavy elements, because no earlier stars had existed to create them. Without heavy elements to help cool the gas, the clouds that collapsed had to be more massive. The first stars, called population 3 stars, were likely dozens or even hundreds of times more massive than the Sun. They burned incredibly hot and bright, lived fast, and died young, exploding as supernovae after just a few million years. These explosions scattered the first heavy elements into space: carbon, oxygen, iron, all forged in the cores of these massive stars. This enriched gas would mix with the primordial hydrogen and helium, allowing the next generation of stars to form with a different composition, beginning the chemical enrichment of the universe. We have never directly observed a population 3 star. They existed so long ago and were so distant that even our most powerful telescopes cannot see individual stars from that era. But we've seen their effects. The James Webb Space Telescope, launched in 2021, is beginning to observe galaxies from very early times, just a few 100 million years after the Big Bang, and is providing clues about the first stars and how galaxies assembled. The Dark Ages are gradually being illuminated. The universe will expand forever, growing colder and darker. Based on our current understanding, the universe will never stop expanding. The discovery of dark energy and the accelerating expansion suggests that the universe is headed toward a cold, lonely future. As expansion continues, galaxies will move farther apart. Eventually, the expansion will carry distant galaxies away faster than light can travel through the expanding space between us, and they'll disappear beyond our cosmic horizon. In a few 100 billion years, only the galaxies in our local group, gravitationally bound together, will remain visible. The rest of the universe will have receded beyond reach. Star formation will gradually decline as galaxies exhaust their gas supplies. New stars will become rarer. In 1 trillion years, most stars will have burned out, leaving behind white dwarfs, neutron stars, and black holes. The universe will grow dark, lit only by occasional flares as old stellar remnants collide or accrete material. Over vastly longer timescales, even these remnants will decay or disappear. Protons, if they're unstable as some theories suggest, will eventually decay, perhaps over 10 to the 34 years. Black holes will slowly evaporate through Hawking radiation, with the largest supermassive black holes taking 10 to the 100 years to disappear. In the unimaginably distant future, the universe will approach a state of maximum entropy, sometimes called heat death. All usable energy will have been dissipated. The temperature will approach absolute zero. Space will be filled with a dilute sea of photons and elementary particles too, diffuse and too cold for any complex structures to form. This future is bleak from a human perspective, but it's so far away that contemplating it is almost meaningless. The universe today is in what might be called its golden age, a brief cosmic moment when stars shine, planets form, and life can exist. We're living in a special time, when the universe is old enough to have formed complex structures, but young enough that stars still burn. If dark energy's nature changes, other fates are possible. If dark energy strengthens over time, the acceleration could become so extreme that it eventually tears apart galaxies, solar systems, planets, atoms, even space-time itself in a big rip. If dark energy weakens or reverses, expansion could slow, stop, and reverse, leading to a big crunch where the universe collapses back into a hot, dense state. But based on current observations, the most likely fate is continued eternal expansion, a slow fade into cold darkness over timescales that dwarf the current age of the universe by factors of trillions of trillions. The Big Bang happened everywhere at once. One of the most common misconceptions about the Big Bang is imagining it as an explosion at a specific location in space, with matter flying outward into a pre-existing void. But that's not what happened. The Big Bang occurred everywhere simultaneously. It was the beginning of space itself, not an event in space. Every point in the universe was once part of the initial hot, dense state. As space expanded, every point moved away from every other point. There's no center to the expansion. From any galaxy's perspective, all other galaxies appear to be moving away, with more distant ones receding faster. This is exactly what we observe. Galaxies in all directions are redshifted, moving away from us. But we're not at the center. An observer in any other galaxy would see the same thing, all other galaxies receding from their location. This is a property of uniform expansion. Space itself is stretching, carrying galaxies with it like dots on an inflating balloon. If you draw dots on a deflated balloon and then inflate it, every dot moves away from every other dot. No dot is at the center of the expansion. The surface of the balloon is the analogy for space itself, and the expansion happens everywhere on the surface simultaneously. Of course, the universe is three-dimensional, not two-dimensional like a balloon's surface, but the principle is the same. This means that asking what the Big Bang expanded into is a meaningless question. It didn't expand into anything. Space itself came into existence and has been expanding ever since. There's no outside, no pre-existing void that the universe fills. Everything that exists is part of the universe, and the universe is all there is, at least within our observable horizon. This is difficult to visualize because our everyday experience involves objects expanding into surrounding space. But the universe's expansion is fundamentally different. It's the expansion of space itself, not motion through space. Understanding this distinction is crucial for grasping the true nature of the Big Bang and cosmic expansion. There may be no before the Big Bang. When we ask what happened before the Big Bang, we're assuming that time extends infinitely into the past. But general relativity, our best theory of space-time, suggests that time itself began at the Big Bang. If there was a true singularity at the beginning, time had a first moment. There's no before because before implies the passage of time, and time didn't exist yet. This is strange and counterintuitive. We're used to thinking of cause and effect, of events having predecessors. But the Big Bang, if it was truly the beginning of time, has no cause in the usual sense. It simply is the starting point of everything, including temporal duration itself. Some physicists argue that quantum effects might avoid the singularity. Quantum mechanics introduces uncertainty, and perhaps that uncertainty prevents the universe from ever reaching truly infinite density. In quantum cosmology, the universe might not have a sharp beginning, but rather emerge from some quantum state that doesn't require time to pre-exist. Proposals like the Hartle-Hawking no-boundary proposal suggest that time might become space-like near the beginning, so that asking what happened before is like asking what's north of the North Pole. It's a meaningless question because you can't go further north than the northernmost point. Other theories propose that our universe emerged from a previous state. Perhaps the Big Bang was a transition, a bounce from a contracting phase. Perhaps our universe is part of an eternal multiverse where universes constantly bubble into existence. These ideas are speculative, extending beyond what we can currently test. The honest answer is that we don't know whether time had a beginning or whether something preceded the Big Bang. Our physics breaks down at the Planck time, and we cannot describe what, if anything, came before. The origin of the universe remains one of the deepest mysteries in science, touching the boundaries of physics, mathematics, and philosophy. For now, we can trace the universe back to an incredibly early moment, but we cannot yet see the absolute beginning, if such a thing exists. The cosmic microwave background will eventually become invisible. The cosmic microwave background has already cooled from 3000 Kelvin at emission to 2.7 Kelvin today, stretched by the expansion of the universe. As expansion continues, the CMB will continue to cool. In a few 100 billion years, it will have redshifted into radio waves with the temperatures measured in millikelvins. Eventually, it will become so cold and diffuse that it will be effectively undetectable. Future civilizations, if any exist trillions of years from now, will live in a very different universe. Most galaxies will have disappeared beyond the horizon. Stars will be rare or extinct. The cosmic microwave background, that ancient light that tells us so much about the universe's origin, will have faded into obscurity. These far future astronomers would have little evidence that the universe had a hot beginning. They might deduce it from theory or find indirect clues, but the direct observational pillars of cosmology, the CMB, and distant galaxies will be gone. This has interesting philosophical implications. We happen to live at a time when the universe's history is written clearly in the sky. We can see the CMB, observe distant galaxies at various cosmic epochs, and reconstruct what happened. We're living in an era of cosmological enlightenment. Earlier in cosmic history, the universe was too young and small for intelligent life to have emerged. Later, the evidence will have faded. We exist in a privileged window, able to observe and understand our cosmic origins. Some have speculated that this is not a coincidence, that the conditions necessary for complex life to evolve are correlated with conditions that allow the universe to be observed and understood. This anthropic reasoning suggests that observers will naturally find themselves in times and places where observation is possible. Whether this is profound or merely tautological is a matter of debate. Regardless, we should appreciate our cosmic vantage point. We can see the universe's baby picture, measure its age and composition, and trace its history from the first moments. This is a remarkable gift, a window of opportunity in the vast sweep of cosmic time. Inflation may have created multiple universes. If inflation occurred, as the evidence suggests, it may have profound implications beyond just explaining the flatness and uniformity of our observable universe. Some models of inflation predict that it doesn't end everywhere simultaneously. In different regions of space, inflation ends at different times. Where it ends, a hot Big Bang begins, creating a region filled with matter and radiation expanding and cooling. But in regions where inflation hasn't ended yet, space continues to inflate exponentially. This creates a picture of eternal inflation, where our observable universe is just one bubble in a vastly larger inflating space. Other bubbles, other universes exist beyond our horizon, each beginning with its own hot Big Bang when inflation ended in that region. These bubble universes are causally disconnected from ours. We can never see them or interact with them because they are beyond our cosmic horizon. The space between bubbles is expanding faster than light can cross it, so signals can never pass between universes. In some versions of this scenario, the physical constants or even the laws of physics might differ between bubbles. Perhaps the strength of gravity, the mass of the electron, or the number of spatial dimensions varies from universe to universe. Our universe, with its particular properties, is one among countless others, each with different characteristics. This multiverse concept is controversial. Some physicists embrace it as a natural consequence of inflation and quantum mechanics. Others reject it as untestable and therefore unscientific. If other universes are forever beyond our observation, can we meaningfully say they exist? And if physical constants vary randomly between universes, does this rob physics of its predictive power, replacing calculation with anthropic reasoning about which universes can support observers? These are deep questions without clear answers. What's certain is that inflation, if it occurred, was a powerful process that shaped our universe. Whether it also created countless others is an open question that may remain forever unanswerable. For now, we can observe and study only our own cosmic bubble, tracing its history from inflation through the present and into the far future. Quantum fluctuations became cosmic structures. One of the most remarkable aspects of modern cosmology is the connection between the smallest and largest scales. Quantum mechanics, which governs the behavior of subatomic particles, played a crucial role in shaping structures billions of light years across. During inflation, quantum fluctuations in the inflaton field, the field driving the exponential expansion, were stretched to macroscopic and then cosmic scales. These fluctuations, originating from the Heisenberg uncertainty principle, were tiny variations in energy density from point to point. As inflation amplified them, they became classical density perturbations, real variations in how much matter and energy existed in different regions. These perturbations are the seeds of all cosmic structure. The slightly denser regions had stronger gravity and pulled in more matter over time. Over billions of years, they collapsed into galaxies, clusters, and the cosmic web. The slightly less dense regions became the voids between structures. Everything we see, every galaxy cluster, every star, every planet, traces back to quantum fluctuations that occurred during the first tiny fraction of a second after the Big Bang. This connection between quantum and cosmic is profound. It suggests that the universe's large-scale structure is fundamentally quantum mechanical in origin. The patterns we observe in the cosmic microwave background and in galaxy surveys are, in essence, quantum mechanics writ large across the sky. This also makes predictions. The properties of quantum fluctuations during inflation are calculable. They should produce fluctuations with specific statistical properties, such as being nearly but not exactly scale invariant, and having a particular distribution of strengths. Observations of the CMB and large-scale structure confirm these predictions, providing strong support for inflation. If we observe deviations from the predicted pattern, it would tell us about the physics of inflation, perhaps revealing new fields or interactions present during that epoch. Future observations with more sensitive CMB experiments and larger galaxy surveys will continue to test these predictions, probing the quantum origins of cosmic structure. The universe is fine-tuned for complexity. When physicists examine the fundamental constants of nature, the strength of forces, the masses of particles, the density of dark energy, they find something puzzling. Many of these values appear fine-tuned. If they were even slightly different, the universe would be dramatically different, often in ways that would preclude the existence of stars, planets, or life. For example, if the strong nuclear force were just a few percent stronger, all hydrogen would have fused into heavier elements in the early universe, leaving no hydrogen for stars or water. If it were weaker, atomic nuclei wouldn't hold together, and chemistry as we know it couldn't exist. If the electromagnetic force were significantly different, atoms wouldn't form or would be unstable. If the cosmological constant, or dark energy density, were much larger, the universe would have expanded so rapidly that galaxies could never form. If it were negative and too large in magnitude, the universe would have recollapsed before stars could form. The masses of fundamental particles also seem finely tuned. If the electron were much heavier, atoms would be tiny and chemistry would be impossible. If the up and down quarks had different masses, protons and neutrons might not be stable. There are dozens of such examples, parameters that seem to lie in narrow ranges necessary for a universe with complexity, structure, and life. This apparent fine-tuning has led to much debate. Some see it as evidence of design, arguing that the universe was intentionally created with these properties. Others invoke the anthropic principle, noting that we can only observe a universe compatible with our existence. If many different universes exist with different constants, we necessarily find ourselves in one of the rare ones where complexity is possible. Still, others hope that a deeper theory will explain why the constants have their observed values, showing that they're not arbitrary, but required by fundamental physics. Perhaps string theory or some future theory of everything will predict the values of all constants from first principles, removing the appearance of fine-tuning. For now, the fine-tuning remains a puzzle. The universe appears balanced on a knife's edge, with parameters lying in narrow ranges that allow stars to shine, planets to form, and life to emerge. Whether this is coincidence, design, a selection effect, or deep physics, we don't yet know. What we do know is that we're extraordinarily fortunate to exist in a universe where existence is possible. The multiverse idea addresses the fine-tuning problem. If eternal inflation creates countless bubble universes with varying properties, the fine-tuning problem has a natural solution. Among the vast ensemble of universes, some will have constants that allow complexity, and those are the only ones that can contain observers. We find ourselves in a fine-tuned universe not because all universes are fine-tuned, but because we couldn't exist in the vast majority of universes that aren't. This is a form of observer selection bias. It's like asking why we live on a planet with liquid water breathable air, and a temperate climate. It's not that most planets are like this. In fact, most aren't. But we can only exist on the rare planets that are. Similarly, we can only exist in the rare universes with properties that permit complexity. This anthropic explanation is philosophically unsatisfying to some. It replaces predictive science with a kind of cosmic lottery, where anything that's possible happens somewhere, and we happen to be where conditions are right. It seems to abandon the goal of explaining why the universe has its particular properties. But proponents argue that it's no different from natural selection explaining biological adaptations. Organisms are fine-tuned for their environments not through design but through selection, and perhaps the same principle applies cosmically. The debate continues. Without access to other universes, we cannot test the multiverse hypothesis directly. We might find indirect evidence, such as signatures of collisions between bubble universes imprinted on the cosmic microwave background, but such evidence would be subtle and controversial. For now, the fine-tuning of the universe remains an open question, a puzzle at the intersection of physics, philosophy, and metaphysics. We may be made of primordial antimatter particles. While most antimatter was annihilated in the early universe, leaving only matter, some antimatter particles survive. Positrons, the antimatter counterparts of electrons, are produced in certain radioactive decays and in high-energy processes. Antiprotons and other antimatter particles are created in particle accelerators and in cosmic ray collisions. But these are newly created, not primordial. There's a more subtle sense in which we might be connected to primordial antimatter. The photons in the cosmic microwave background, which fill all of space, originated from matter-antimatter annihilation in the early universe. When matter and antimatter particles met and destroyed each other, they converted their mass into energy, into photons. These photons are still around. For every atom in the universe today, there are about 10 billion cmb photons. These photons carry the energy of the matter and antimatter that annihilated. In a sense, they're the ashes of that cosmic fire. When you stand in the sun's warmth or look at a distant star, you're experiencing electromagnetic radiation, photons produced by nuclear fusion. But space itself is filled with photons from an even earlier source, from the annihilation of matter and antimatter in the first seconds after the Big Bang. These photons have cooled and stretched into microwaves, but they're everywhere, passing through you constantly. In a poetic sense, we're surrounded by the remnants of antimatter, by the energy released when the universe purged itself of that primordial symmetry, leaving the slight excess of matter from which galaxies, stars, planets, and life would eventually form. This connection between the ordinary matter that makes up our bodies and the antimatter that once existed equally is a reminder of the universe's violent, energetic past. Everything we see today is the residue of those first moments, the tiny imbalance and the enormous energy release that followed. The Big Bang created space, time, and energy simultaneously. When we think about the Big Bang, it's tempting to imagine time already existing, with the universe suddenly appearing within it. But that's not accurate. The Big Bang was the origin of time itself. Before, if that word even makes sense, there was no time, no duration, no sequence of events. Space, time, and energy all came into existence together, or perhaps they transformed from some prior quantum state that we don't yet understand. This means the universe didn't begin at a moment in time. It began as time, with time itself emerging along with space and energy. This is one of the deep insights of general relativity. Time is not an absolute background against which events occur. It's part of the physical universe, inseparable from space, forming the four-dimensional fabric of space-time that can stretch, curve, and even begin. Understanding this requires letting go of intuitions built from everyday experience. We're used to time flowing steadily, with events happening in sequence, causes preceding effects. But at the origin of the universe, these familiar concepts break down. Causality, the arrow of time, the distinction between past and future, all of these emerge from the structure of space-time itself. If space-time had a beginning, these concepts don't apply before that beginning. Quantum mechanics adds further complexity. At the Planck scale, quantum fluctuations of space-time itself become important. Time might not be smooth and continuous, but grainy and uncertain. Some theories suggest that time might be emergent, not fundamental, arising from deeper quantum structures. These are speculative ideas at the frontier of theoretical physics. What's clear is that the Big Bang was not an event in time, but the origin of time. Asking what caused the Big Bang, or what happened before it, may be like asking what's north of the North Pole. The question assumes a framework, a direction of time that doesn't exist at the boundary. Perhaps the universe simply is, with no external cause, no prior state, no explanation beyond the laws of physics themselves. Or perhaps our universe emerged from something else, a quantum vacuum, a previous universe, a higher dimensional structure. We're probing the limits of knowledge, the boundary between physics and metaphysics. Neutrinos from the Big Bang surround us. Just as the universe is filled with photons from the cosmic microwave background, it's also filled with neutrinos from an even earlier time. The cosmic neutrino background, or CNB, consists of neutrinos that decoupled from other matter and radiation about 1 second after the Big Bang, when the universe was around 10 billion degrees. At that temperature, neutrinos were produced copiously and interacted frequently with other particles. But as the universe expanded and cooled, neutrinos began to interact too rarely to stay in equilibrium. They decoupled, streaming freely through space. Since then, they've been traveling unimpeded, cooled by cosmic expansion just like the photons of the CMB. Today, the cosmic neutrino background should have a temperature of about 1.9 Kelvin, slightly cooler than the CMB because neutrinos decoupled earlier when the universe was hotter and have been diluted more by expansion. There should be about 300 million neutrinos per cubic meter of space, about 50 times more numerous than CMB photons per cubic meter, though photons dominate the energy density because neutrinos have tiny masses. The cosmic neutrino background has never been directly detected. Neutrinos interact so weakly that detecting primordial neutrinos, which have extremely low energies, is beyond current technology. But we're confident the CNB exists because the physics is straightforward. Neutrinos were produced in the early universe, they decoupled at a predictable time, and they've been cooling ever since. The CNB affects cosmology in subtle ways. Neutrinos contribute to the total energy density of the universe, affecting its expansion rate. They also affect structure formation. Because neutrinos move at nearly the speed of light even today, they smooth out density fluctuations on small scales, suppressing the formation of the smallest dark matter halos. By measuring the distribution of galaxies very precisely, cosmologists can infer the neutrino contribution and even constrain the sum of neutrino masses. Future experiments might detect the cosmic neutrino background directly, perhaps through its effects on tritium decay experiments or through gravitational effects. If we could detect it, the CNB would provide a view of the universe at 1 second old, earlier than any other observable signal except possibly primordial gravitational waves. It would be another window into the earliest moments of cosmic history. We live in the universe's middle age. The universe is 13.8 billion years old, ancient by human standards but relatively young compared to how long it will exist. If the universe continues to expand forever, and if stars continue to form for another trillion years, then we're living in the first couple percent of the era when stars shine. In a sense, the universe is still young, still in its vigorous star-forming prime. But compared to the first few 100 million years when the universe was devoid of stars, we're living very late, long after the initial burst of structure formation. From this perspective, the universe is already mature, with its large-scale structure mostly in place. Perhaps the best way to think of it is that we're in the universe's middle age. The violent, chaotic early times have passed. The first stars have formed, died, and enriched space with heavy elements. Galaxies have assembled and are still evolving through mergers and star formation. Planets have formed around long-lived stars, and on at least one, life has emerged and become intelligent enough to ponder its origins. The universe is settled enough for complexity to arise, but still active enough for new structures to form. In the far future, this era will be remembered, if anyone is around to remember, as the Golden Age. A time when stars were abundant, when galaxies filled the sky, when the cosmic microwave background was still detectable, when the conditions for life were optimal. We are fortunate to exist now, in this brief window between the chaos of the beginning and the cold darkness of the far future. Our existence is a product of cosmic evolution, atoms forged in stars, planets formed from the debris of earlier generations, life emerging from chemistry and evolution. We are the universe become conscious, a way for the cosmos to know itself, as Carl Sagan said. And we live at a moment when the universe's story can be read in the sky, when ancient light and distant galaxies tell us where we came from. The Big Bang explains the 3 pillars of cosmology. Modern cosmology rests on 3 main observational pillars, 3 independent lines of evidence that all point to the same conclusion. The universe began in a hot, dense state, and has been expanding and cooling for billions of years. The first pillar is the expansion of the universe, discovered by Hubble. Galaxies are moving away from each other, with distant ones receding faster. This implies the universe was denser and smaller in the past. The second pillar is the cosmic microwave background, the afterglow of the Big Bang. This thermal radiation fills all of space and matches the predicted properties of light released when the universe cooled enough for atoms to form. The third pillar is the abundance of light elements, hydrogen, helium, and traces of deuterium and lithium exist in proportions precisely predicted by nuclear physics in the first few minutes after the Big Bang. No other theory explains all 3 observations. Steady-state models can't account for the CMB or element abundances. Models without dark matter can't explain galaxy rotation curves or structure formation. Models without dark energy can't explain the accelerating expansion or distant supernova observations. The Big Bang theory, supplemented by inflation, dark matter, and dark energy, explains everything we observe. The agreement between independent measurements is stunning. The baryon density inferred from Big Bang nucleosynthesis matches that measured from the CMB. The age of the universe, calculated from expansion, matches the ages of the oldest stars. The predictions of inflation match the observed properties of CMB fluctuations and large-scale structure. This convergence of evidence from multiple independent sources is what gives scientists confidence. When different methods, based on different physics, all point to the same answer, that answer is likely correct. The Big Bang theory has been tested more rigorously than almost any theory in science. It makes precise, quantitative predictions that have been confirmed again and again. This doesn't mean we understand everything. Dark matter and dark energy remain mysterious. The very earliest moments, the Planck era, are beyond our current physics. The nature of inflation and the possibility of a multiverse are speculative. But the basic framework, that the universe began hot and dense and has been expanding and evolving for nearly 14 billion years, is as well established as any scientific theory. We may never know why the Big Bang happened. Science is powerful, but it has limits. We can trace the universe back to the tiniest fractions of a second, describe conditions at unimaginable temperatures and densities, and predict the outcomes of processes that occurred billions of years ago. But when we ask why the Big Bang happened, why there's something rather than nothing, why the universe exists at all, we reach the boundary of scientific inquiry. These questions may not have scientific answers. Science describes how things happen, the mechanisms and laws that govern physical processes, but it doesn't necessarily explain why those laws exist or why the universe follows them. Perhaps the universe simply is, with no deeper explanation. Perhaps existence is the default state, and nothingness is not even a coherent concept. Perhaps our universe is one of many in a vast multiverse, and asking why it exists is like asking why a particular atom exists when countless others do. Perhaps there's a deeper theory, a final theory of everything, that will explain the universe's properties as inevitable consequences of mathematical consistency. String theorists and others hope to find such a theory, showing that the universe had to be this way, that no other universe is logically possible. Or perhaps the question has no answer, at least not one accessible to human minds or scientific methods. We might be asking something fundamentally unanswerable, constrained by our nature as finite beings within the universe, trying to understand the universe as a whole. This isn't a reason for despair, but for humility and wonder. The fact that we can ask these questions, that we can trace our origins back to the first moments of creation, that we can measure the universe's age and composition and predict its fate, is extraordinary. We are pattern-seeking creatures, evolved on a small planet, using instruments and mathematics to peer across billions of light years and billions of years, reconstructing a history that encompasses everything. Even if we never answer the ultimate why, the how is endlessly fascinating. And the journey of discovery, the process of learning how the universe works, is perhaps meaningful in itself. We are the universe's way of understanding itself, and in that understanding we find beauty, wonder, and connection to something vastly larger than ourselves. And now the universe begins to settle in your thoughts. We've journeyed through time itself, from the inconceivable beginning to the present moment. From infinite density to vast expanding space, from pure energy to matter and stars, from chaos to structure, from simplicity to the complexity that allowed life to emerge. You've heard of quantum fluctuations that became galaxies, of sound waves in primordial plasma that left patterns we can still measure, of the first stars lighting up the darkness, of the cosmic web connecting everything across billions of light years, of dark matter and dark energy, invisible forces shaping the cosmos. You are part of this story. The atoms in your body were forged in stars that exploded billions of years ago. The oxygen you breathe was created in massive stars. The carbon in your cells was built up through nuclear fusion in stellar cores. The iron in your blood was created in supernova explosions. You are literally made of stardust, assembled from the ashes of stars that lived and died long before the sun was born. The hydrogen in your body, simple protons, those have been around since the first few minutes after the Big Bang. Some of the hydrogen in the water you drink, in the molecules of your body, is primordial, unchanged since it formed 13 billion years ago. You carry within you atoms from the beginning of time. Tonight, as you rest, photons from the cosmic microwave background pass through you, ancient light from when the universe first became transparent. Neutrinos from the sun and from distant supernovae stream through your body by the billions. Gravitational waves from merging black holes ripple through space, compressing and stretching everything by imperceptible amounts. You are part of the universe, made from it, immersed in it, connected to everything through shared history and physical law. The universe is not something separate, something out there to be observed. You are the universe observing itself. Consciousness arose from matter. Matter arose from energy. Energy arose from the quantum fields of the early universe, and all of it traces back to that first moment. The Big Bang, the origin of everything. As you drift toward sleep, imagine yourself expanding backward through time, through your childhood, through your birth, through generations of ancestors, through the evolution of life on Earth, through the formation of the planet from a disk of dust around the young sun, through the collapse of a gas cloud that would become our solar system, through billions of years when the galaxy was younger and stars were forming, through the assembly of galaxies from smaller fragments, through the first stars lighting up the darkness, through the dark ages when no light shone, through recombination when the universe became transparent and the cosmic microwave background was released, through the formation of the first atoms, through Big Bang nucleosynthesis when hydrogen fused into helium, through the first seconds when quarks confined into protons and neutrons, through the first microseconds when the universe was a quark-gluon plasma, through the first tiny fractions of a second when inflation stretched space exponentially, back toward the beginning, toward the moment when space and time and energy all emerged together, toward the ultimate mystery, the origin of everything. You are connected to that moment. You are made of it. You are a pattern that the universe formed, a temporary arrangement of matter and energy that can think and feel and wonder. And in wondering about the Big Bang, about where you came from, you're participating in something profound, the universe's long journey toward understanding itself. Rest now. Let these thoughts fade like the cosmic microwave background, cooling and stretching into the distance. Let your mind grow quiet like the universe after the chaos of its beginning. You are safe. You are part of something ancient and vast. You are home. If you're still awake, you can continue to the next chapter now. But if sleep has found you, then welcome it. Dream of stars and galaxies, of ancient light and the deep mysteries of existence. Dream softly. Good night.